I'm very happy to be here to share my work titled Diffusion Backbones of Temporal High-Order Networks. This is a joint work with Dr. Alberto Zero, who is a postdoc in Leiden University, and my supervisor, Dr. Huijun Wang. So first of all, I would like to introduce briefly what is a temporal high-order network, in case some of you are not familiar with this. So we represent a temporal high-order network with a temporal hypergraph. You can like this is a simple example of a temporal high-order networks, which have in total 8 timestamps, and each timestamp corresponds to a snapshot of the temporal high-order network. For example, in the first snapshot here, there are two time-respective interaction. One interaction is a order 2 interaction between node 1 and node 4, and the other interaction is among the other 3 nodes. So there is a order 2 hyperlink and a order 3 hyperlink in the first snapshot. So for any given temporal high-order network, we can have a temporal time aggregate network, which is a weighted hypergraph. Here you can see that, and this is actually a graph that we can obtain by aggregate the original temporal high-order network along time dimension. So the time aggregate network have the same set of nodes as a temporal high-order network, and each hyperlink in the time aggregate network is also aligned with a weight, which represents the number of activations of this hyperlink in the original temporal high-order network. So we denote the weight as a Wj here. So we study the contagion process on temporal high-order networks. So what we do is that we adapt a susceptible infected threshold process, which has been already studied in a previous literature. So in this process, we assume that there is one SIG node in the beginning at the initial time t0. When there is a hyperlink active at any given time t, if the number of infected nodes within a hyperlink is larger than threshold theta, then each of the susceptible nodes in the hyperlink can be infected independently with infection probability at the next timestamp. This is a contagion process. And let's look at a simple example. We assume that we use node 1 as the only SIG nodes, and we set the threshold to 1, and beta, the infection probability is 1. So it's a deterministic case. Like at the t0, node 1 is infected. At the first timestamp t1, node 1 has a contact with node 4. So in the next timestamp t2, node 4 is infected. And at this time 2, node 4 has a order 3 hyperlink interaction with node 2 and node 5. So at the time t3, node 2 and node 5 get infected. Then node 2 and node 5 have an interaction with node 3, so node 3 gets infected in the next step. So at time t4, the process finished because all nodes get infected already. So that's when the threshold is a bit larger, we set it to d-1, which means that the threshold equals to the size of the hyperlink -1. What does it mean? That, like, for example, at the timestamp t2, only node 4 is infected in this order 3 hyperlink. So, but for order 3 hyperlink, it requires 2 nodes to to be infected to infect the other susceptible nodes. So it cannot infect node 2 and node 5 in the next time step. But at T3, node 4 has a pairwise interaction with node 5. For order 2 hyperlink, so the threshold is 2 minus 1, so it's 1. So node 4 infects node 5 in the next time step. So for different thresholds, a diffusion may follow different diffusion trajectories. Yeah, this is an example of a contagion process on temporal high order networks. Now we have defined the temporal high order networks and the contagion process on this temporal high order network. So our question is that which hyperlink contribute more to the diffusion process? Or we can say we can define the contribution of a hyperlink as the number of nodes that are affected directly through a hyperlink. So we also would like to know that which property of the hyperlink in the temporal high order network can be used to estimate the contribution of the hyperlink. So yeah, the next question is which property of a hyperlink correlates the most with the contribution of the hyperlink. So in order to do so, we first encode the contribution of each hyperlink by a diffusion backbone. So what is a diffusion backbone? Let's look at the previous example of temporal order network. We have this network, and in case of theta equal to 1 and beta equal to 1, we select each node in the temporal order network as a seed node. Then for each seed node, we can construct a diffusion trajectory. Then we have in total 5 trajectory. And the diffusion backbone is then defined as a union of these 5 diffusion trajectory. And then each hyperlink in the backbone here is also aligned with a weight, which represents the average number of nodes that are infected by directly through the hyperlink. Yeah, in the same way, we can also define the diffusion backbone using different thresholds. So that we can see that different thresholds correspond to different topology and in the diffusion backbone. Yeah. So we study the diffusion backbones of 8 empirical data sets, which represent face-to-face high-order interactions of human. So these data sets can be downloaded free in this website. We can see that in each data set, order 2 and order 3 hyperlinks are the most frequent in the among all the orders. So we first study the limiting case when beta approaches 0. By using some basic probabilities, we can show that when beta approaches 0, the weight of a hyperlink in the backbone can be approximated by these formulas. Like when theta equal to 1, the weight of a hyperlink in the backbone is can be approximated to the order of to the order of beta, which means that it is proportional to beta and also proportional to the weight of the hyperlink in the aggregate network. But for theta equals to d minus 1, it's a little bit different. For order 2 hyperlinks, it's the same with the case of theta equal to 1. But for hyperlinks of higher order, for example, order 3 hyperlink, it can be approximated to the order of beta squared, because when beta is very small, assume that there is a seed node in the order 3 hyperlink. It cannot be used to infect the other 2 nodes directly. Otherwise, because the threshold is 2 for all the 3 hyperlink. So in this case, it requires that one of the 2 other nodes in this hyperlink need to be infected through other hyperlinks first. Then the target hyperlink can be used to infect the component nodes of this hyperlink. So as we can see that here, as beta approaches 0, when theta equals to d minus 1, which correspond to the dashed lines, the contribution of all the 3 hyperlinks approaches 0. This is because that all the 3 is negligible small compared to other 2 hyperlinks. Yeah, but as beta increases, the contribution of all the 3 hyperlinks increase to a non-zero value because the infection nodes in the process increases and more high-order hyperlinks are used to infect those. Yeah. So next, we would like to study which property of the hyperlink in the high-order network can be used to estimate the so-called contribution of the hyperlink in the backbone. So in order to do so, we propose a centrality metric for hyperlinks. And first, we define a set of for any given target hyperlink, we define a set of hyperlink which contains all order 2 hyperlinks that share at least 2 nodes with the target hyperlink. So with this definition of this hyperlink set, we define the first metric called the static metric, which is the weight of the hyperlink times the summation of the weights of hyperlinks in this set plus 1 to the power of alpha. So it's here alpha can be regarded as a scaling parameter. If we take a log scale logarithm on both sides, we can see that alpha is actually a weight which assign the importance of this term, which represents the influence of the hyperlink in this set. So we also propose a temporal metric, which represents which is just a generalization of this static metric, because we can see that here is actually the number of activations of the target hyperlink J in the high-order network times the total number of activations of the hyperlink in this set. So we pose a constraint that the activation of the hyperlink in this set should be before the activation of the target hyperlink Hj. So, yeah. So here I show the correlation between the proposed centrality metric of a hyperlink with a weight in the backbone. We can see that when beta approaches 0, the weights Wj in the aggregated network performs the best when theta equals to 1, which is consistent with our analysis in the limiting case beta approaches 0. When theta equals to d minus 1, however, the proposed metric performs the best when beta equals to 0. This is because that for high order networks, the activation, the hyperlink if the hyperlink need to be used in the diffusion process, then the hyperlink the coordinate nodes of the target hyperlink need to be infected by the other hyperlink first. Yes. So this is our basically all the results. First, we propose the concept of diffusion backbones, which characterize the contribution of each hyperlink in the temporal held network. And second, we analyze the backbone in the limiting case. And we propose some centrality metrics to estimate the contribution of a hyperlink in the temporal held network. Of course, in the future work, we think that the future backbone can be generalized to other dynamical process, not only the contingent process. And yeah, and also we can do additional analysis on other types of high order interactions like scientific collaboration. Yeah. Thanks for your attention.